this is the method, iterative way, how we can compute uh, the value at a particular state, and which is the maximum uh, possible return again in the probabilistic sense. As you can see that in this particular expression, we are considering there are two parts. One is that the return what you are getting at that point due to the action A on state S. Okay, so since it is probabilistic, since there is a distribution, so you are considering the expectation, so expected return based on that. And the other part is a discounted, return because of your series of actions from that point. So, which means that no, because of your action, you will have state transitions, and uh, I mean it goes, but since it is a dynamic programming based approach, you have also the respective prospective return at that state. So you simply use that for the discounted return. So you know that what is the maximum possible return, expected return from state S prime, for example, if your transition to state S prime. So you uh, you just consider the discounted return. So gamma is the discounting factor. So gamma is a fraction. So fraction of that return you are adding with the immediate return what is expected at that point. And naturally, since you have a probability distribution, so you are using it uh, to once again to take the average of such return or expectation of such return at because of the state transitions. So this is the interpretation of this particular equation, and so the action which maximizes this, that would be the maximum value at that point for the state, maximum possible return at that point. And you also store the corresponding action because that is required for storing the policy, for determining the policy, that what action you should take if you reach at state S. That is interpretation. So if you get the policy, so that is exactly what is your learning. So you can, for an unknown scenario, you can use that policy to choose an action, and in that way you are trying to reach a certain goal state or trying to maximize your rewards. So this learning, as you see that uh, because it's iterative, and you can design an iterative algorithm so that no, you can start with certain arbitrary values of each state, and then through iterations you can converge. You can converge to those mm, sorry, to those states. So initialization is once again is one issue uh, for this convergence. So depending upon the domain, you have to choose a proper initial value. Otherwise, you can consider all of them are starting with some arbitrary number. As you can see, and of course there is also the rewards, that model is also there. So since it is adding, even if you start with all zero, it does not matter. You will get convergence to a particular state, but it may not be unique, as you understand that. So there are two approaches. One is value iteration algorithm. The other one is policy iteration algorithm. In value iteration algorithm, you converge over the values, and that means no, you are determining these values, and then you are also updating the policies, but your convergence is tested over the values of its at each state. Whereas in policy iteration algorithm, your convergence is tested over the policies. So that is the difference. So this is your value iteration algorithms. As you can see that you are both storing the updated value and also updated action for state S, and that is what is your policy. But no, you are stopping at the convergence of the values of each state. Whereas in policy iteration algorithm, you are converging over the policy. That means you can, once again, you can initialize pi to arbitrary values and use them to choose action. So you can use them to choose action for choosing the values itself, right? So that is what we will be doing. And so in this case, as you can see that the policy is guiding you to compute the maximum possible values at each state given that policy. And then, of course, whenever you are choosing an action, and immediately you are updating also your policy. So you go on doing these things until you reach at a convergence. So these are the things we discussed in the previous class itself. I just have once again just recapitulated what we discussed, just to have a better continuity of our discussion. So now we will consider the other scenario when there is no prior knowledge of the model. That means you do not have those probability distributions for rewards and state transitions given the state action pair. So this is what you do not have them. So how do you, in that case, how do you explore this scenario? If you remember that, when we discussed about a very simple model of the K-arm bandit problem, very simple model. There is only one state and you are choosing a lever. So there also, if you can get probabilistic reward given some action. That means there is a probability distribution, so reward may not be deterministic. So what we have done, instead of computing explicitly the probability density functions to find out the expected reward for an action, there we have maintained a running average. Now that is very simple because you do not require to know the distributions, explicit distribution for that reward given an action. But no, if you observe sufficiently over, I say, many instances of that action, and if you observe what rewards you are getting, you can simply consider take the average of them, and that is what you consider, that is your expected return. So trick here is that because average computation is instantaneous, average computation was simple. So you are basically updating your instantaneous average by a weighted average. So what is the present average? And then you are simply, whenever you are getting a new value, you make a weighted average. So learning factor, we call it, actually that weight is a learning factor. So you add the difference of the reward and the present average, certain fraction of it, which is equivalent to the weighted average. I mentioned that also. So we'll see actually that policy, that simple policy is also adopted here. Only in this case, since you have number of states, so for every state action pair, you do the same thing. You do the same thing. That is one thing. Second thing is that since there are a number of states, in the previous case, state transition was not an issue, but here the state transitions are also issue. That means you should consider different series of state transitions and consider what should be your maximum possible running average. So that question is also there. So let us see how those two things are adopted, or rather adapted under this scenario from that simple concept. So we require to explore to see the value of the next state and reward. That exploration means exactly that's what I mentioned, that you check from your experiments that what you are getting, what is the reward you are receiving, what is the state it is making a transition for your operations, and then you note them, and then you maintain you maintain the values based on that operations. Here also, see, we will be considering, since we are maintaining only running averages, and it is possible to have once again the discounted framework of that. So we can update that thing here. And we call them temporal difference because of that. As you understand that now we are adding the difference of reward and what was previous value. That difference, a fraction of that we are adding. So we are considering instances means with time instances. So with time you are exploring. So we call them as each trial is a time point at a discrete time points. So that's why the temporal difference, the term is used for this kind of approach. We call them as temporal difference algorithms. So which means it examines the difference between current estimate of the value and the discounted value of the next state and the reward received. So once again, if the environment is deterministic, you have a simple situation. In the previous K-arm bandit case, if it is deterministic, you can stop it after, if there are K levers, you can stop after observing for each lever, and you know what reward is coming, and you can take a decision. But no, since you have many states, it's not so simple, because finally it is a series of state actions that would determine what would be the reward. So that's why, though it is deterministic environment, but no, things are much complex here. So iteratively you have to do it. Once again, you have to follow the iterative approach, because you need a convergence for that. So you can start with some arbitrary values. Now in this case, we will be considering rather, instead of storing value of a particular state for every possible actions, a maximal we will be considering only, we'll be factorize them. We'll be factorizing them. So we'll be considering storing individually state action pairs. Finally, value at the state would be the maximum of that, values of each state action pair. So that is the definitions we have already seen. So we'll be working on that Q values. No? We have identified this function. One is V function, that is for value, and Q function is value, once again same value function, but here the argument is a state action pair. In the previous case, the argument was just state. So this is exactly what I mentioned for deterministic environment. So you can see that you are iterating over that. You are adding the maximum possible return for an action of the, when you take an action at that point, and what is the possible state transitions from that. So if you consider, if you consider a state transitions ST, and due to your action, you are considering what is the, due to your action you have an ST plus 1. So now ST plus 1 can take also AT K, say suppose there are K actions, so K possible actions. So AT plus 1 denotes, so out of them, which is giving the maximum Q value. So that discounted return you have to consider, and the reward you receive due to the action AT on ST, right? So you understand that because of the action AT on, that is AT is a, T is here is a subscript. So you should, my pronunciation, you should take it like this. So AT, when you act with AT at ST at the Tth time point, you get a reward which is now starting from the T plus 1th time point. Now also it gets a state transitions to ST plus 1. Right? So these are all deterministic. ST plus 1 is also deterministic. You have a lookup table. If you make an action AT on ST, there would be a stretch transition, which is also known to you ST plus. That is denoted by ST plus 1. Now, with that state transitions, at that state ST plus 1, again, there are possible K actions, if there are K finite actions. So which action is giving you the maximum Q value? Discount that. Get the discounted value added with the immediate reward. Exactly. So this is the iterations you will be doing, and you should update at every exploration. So you should note also. So you are doing these things. Finally, you can find out that at each state which action is giving the maximum reward, and you are storing it as a policy. So once again, the convergence is a issue here, and once you converge when all pairs are stable, that means little changes in iterations, then only you stop the updates, and you also choose the policy, optimal policy, by observing that for each state which action is giving you has the maximum Q value. So that is that is how the optimum policy is retrieved. Now this is the deterministic framework, and here things are though not as complex as non-deterministic, where you are maintaining running average, etc. You are not maintaining here in this case. No, you are not considering running average in the sense because it is deterministic. RT plus 1 is very fixed, whereas ST plus 1 is also fixed in this iteration. So only thing is that convergence is an issue because you do not know initially what values will be consistent with the state transitions and revert giving, because there has to be a stable state. Stability should be achieved. So you start with any arbitrary values for each state action pairs, and you go on iterating till you get a convergence. So at that point, you know that there won't be any change. I mean, the system has become. So this is from there you can make a frame a policy. That means policy means what action in a particular state. Now, when we are considering the non-deterministic environment, in this case, as you understand that rewards will vary, state transitions will vary. So we'll follow the same. So we do not know their probability distributions, but no, we can observe and we can always record the maximum possible reward possible. So we maintain the running average of maximum reward at that point for that state action pair. Next instance, when you observe, you find out you get what reward, you get what discounted value. Once again, you just update it. So it's difference. So here, instead of observing like in the previous case of I should say the simple case of KR mandate, you are just considering reward. But as I was mentioning, in this case, not the immediate reward only, it is immediate reward plus discounted, return from the series of actions. So these two would make you will give you the prospective reward. So you are keeping the running average of prospective reward at every state action pair and use the same update rules, which is basically weighted average. That means take the difference of the reward present next the reward received and what was the previous running average. Take this difference. So not only reward received plus the discounted reward from the prospective actions for state transitions. Once again, you have to consider the maximum, which state transitions will give you the maximum reward. So you consider that, and then you take the difference from the present average, add the fractional value of that. So this is what you are doing. So you see that this is exactly I mentioned that you consider you consider that you are considering the maximum. See, this is a learning part, and this is the discounted part because you have observed both. See what you have observed. You have observed RT plus 1, and also you have observed ST plus 1. So you are exploring it. So when you have taken an action AT on ST, like in ST, if you have taken action AT, you have observed RT plus 1, ST plus 1. So since you know ST plus 1, now you consider all possible actions at ST plus 1 and take the maximum of it and give the discounted reward, add with this immediate return. So this is the value what you are getting, right? This is the value what you are getting for this exploration. Take the difference from this with the present value and add the fractional value of it. You can see that actually it means that you are doing 1 minus theta of, I mentioned earlier also, but I did not write this equation, so I'm writing it once again. Q at that state action pair into theta of this cumulative value, right? So So this is the weighted average I'm talking about. This is a running average of the value. So this is what you are getting at that point because of these actions, and this was your stored value. So you go on doing this kind of iterations, and at every explorations, finally, when it converges for every possible, every state action pairs, then you stop. So this is called actually delta rule once again. One of the thing is that sometimes instead of so when you are computing the next action, it is because it's a exploration, you have to have also certain policy. So which action you should explore. Now naturally, the idea would have been that no action which is giving me so far maximum return at that state I should choose. Now the thing is that in that case, no, if I deterministically, if I choose that one, so I will always get the same series of actions. My exploration of the state action space, if I consider state action space, my exploration in that space would be limited. I mean, we will be basically observing a certain part of it, and you may not get the actual maxima. You may be stuck at that point. So what you should do, you should have some randomness. So there, you make a probabilistic way of choosing an action. So more, so if there are set of actions, each one will give you certain return. You should probably still select in proportion to their return. That is that epsilon greedy sampling. So epsilon greedy sampling, say first that no, you sample an action uniformly with a probability epsilon initially. Initially epsilon uniformly with a probability epsilon, and then actions providing higher values would have higher probability, right? Actions providing higher values would have higher probability uh, for following. So you can use softmax over Q values. So that's a very standard trick, and you can use a soft, but you can see that there is a factor like in simulated annealing what we do, that there is a this return Q value is divided by the factor T, which is called temperature, right? So as you gradually increase with the increase of time, you also increase this, uh, uh, you decrease this temperature. Yeah, because if temperature is very high, then it is going to be more uniform. But if temperature is so as every iteration T increases, favoring higher Q value. Right. So sorry, you are increasing temperature. Hmm. I have to check this part. Huh? I will. Just a minute. Let me check. I have some doubt. Yeah, I was wrong in this slide. So T should decrease. T should decrease favoring higher values, right? So it should be decreasing value. As we understand that, because if uh, T is very high means it is uniform probability, right? Sorry, you take it as decreasing value. So T should decrease. Every iteration T would decrease and it will favor higher values, and no, you should stop when T is very small. So this is how you do it, um, right? You start with a very large T, but uh, you decrease it, and finally you stop when the T is very small. So you are also sort of guaranteeing the convergence of this particular process. Now, so this is how we basically uh, learn the Q values, and from Q values, you know that once you have the Q values, then you can frame the optimal policy for every state. You find out which action is giving the maximum return, and in a policy, you should assign that action to that state, right? So this is what you do. There are certain issues, of course. System may be very complex, where no, you have a very large number of states and actions. Then this particular type of algorithm is not very suitable, in the sense that, as you have seen, that we have to store the state action pairs, um, values. So which means in a form of a table you are doing it, and then since you are choosing maximum, you have to make a kind of tabular search. Of course, you can use some efficient data structure for finding the max, like you can use some heap kind of data structure, etc. But still, for a large number of states and actions, once is the requirement of storage would be very high. So that is one problem. The other, even the process is also time consuming. So there, and usually in the reinforcement learning, usually the systems, realistic systems, or problems what you would like to solve, you will face this problem. It has large number of states. So one of the thing, what you, in that case, what is done, you can use certain regression. So uh, instead of making a tabular search, storing all values and then make a search to get the value, you can develop the regression model, because you are observing. So those are the data you are getting. So you can predict for you can develop a model out of this using some parameters, with some parametric, some kind of parametric modeling for that state, and you can predict what should be your so in the policy itself, when you are considering the state and reward transition, so you can predict those things. You can predict your reward and next steps at that state itself. So you require supervisory information or labels, of course, but that you consider, you take it from the exploration itself. So I'm not giving details on this part. So this is reinforcement learning itself is a very involved subject, and in fact there is a separate course what is offered from our department. I think it is the next semester, so you can take that course also, where under deep learning framework also reinforcement learning is considered. So just to summarize once again on this particular topic, that reinforcement learning means it is learning with a critic, and which is different from supervised learning that we have seen, because a critic does not tell you how to do it, it only evaluates your performance, and based on that, an agent is learning how to interact with the environment to maximize the reward or to reach a goal state. So that is what labels or end results are directly not available, but an agent observes state changes on actions and may get reward from a critic. So using this, the agent is learning. It may be non-deterministic as well, as we have seen. And under this, the major objective here is to determine a policy. Like in supervised learning, you have seen that one of the major objective is classification, right? The other objective was, of course, regression. These are the two. Classification and regressions are the major task there. Similarly, in the unsupervised learning, you have considered grouping of similar data, clustering. That is the, I should say, the main task, or that is the task what we do. In reinforcement learning, we learn a policy. We learn a policy how to interact with an environment given its states, given its conditions, what action we should choose. So that is what, and that we learn, and then no, for an unseen cases like no, when and freely an agent is interacting, guided by this policy, the actions are taken. So these are the, no, I hope I have made a bit more clear that why reinforcement learning a bit different paradigm. We cannot call it supervised, neither we call it unsupervised. It is something a bit different, a very close, some similarities with supervised learning, because no, you get some information, you are using some information from the environment, from the critic, but it is not as no explicit as from a teacher. So, so objective here is that you want to reach a goal from any arbitrary state, from a state. And we have considered some approaches for learning this policy, and two particular types of approach. One is model-based learning, where you have value iteration and policy iteration. These are two ways of, two ways of learning the policy, if I say. And then the other approach is temporal difference algorithms, where you do not have the model of the probabilistic model of rewards and state transitions, but by observing, by exploring, you are maintaining running averages of your prospective returns for state action, every state action pair, and finally when you are using them to frame a policy. So you have both deterministic and non-deterministic conditions here, and the kind of approach what I mentioned, the algorithm, learning algorithm, what I consider, that is also popularly known as Q learning. See, all these terms, they get very standardized, and you will rather, instead of calling them temporal difference algorithms, you will rather hear the term Q learning with that delta rule in that respect. So with this, let me stop here for my lecture. In fact, as I mentioned, that this is your last topic for your course, and in fact today is in that way is the last class covering any particular topic. So next week on Wednesday we'll have a class, and that class will be a kind of a doubt clearing session. So I will see that I would like to, I will be interacting with you in the doubt clearing session. But after that, there will not be any class. I will give you off, and you can interact with TAs, etc. in between. And then your examination, or rather the third quiz, that will be held on 18th November, as I declared earlier. So that would be, once again, it's a Thursday, which means it is 12. You take 10 minutes gap, because you can join it comfortably, join the quiz. So 12:10 to 1:10. So it is 1 hour. Your topic is after the second quiz, whatever has been covered. So which means, as I remember, it starts with this, that is what we call dimension reduction techniques, principal component analysis, then linear discriminant analysis. And then we have discussed about linear discriminant functions, then support vector machines. We have also considered artificial neural networks, and then I think ensemble learning, reinforcement learning. You check the list of topics, what has been covered after the second, all of them. If I have missed any topic, uh, I mean, you should consider them also, which is covered after your second quiz. They are part of your syllabus. So thank you very much for attending this course, and let me know if you have any particular doubt today itself. I'll be very happy to take any question.